Hi there, folks. Today we're going to talk about Module 6, Graph Theory and Abstract Algebra. And this will just be a brief introduction. And so, graph theory is the study of connection. Whether we're dealing with organizational trees or sports schedules or road systems or the human anatomy, the structures in place are generally the same and can be modeled using graphs. These are not your traditional graphs. These are graphs which are created by using vertices and connecting edges. We'll discuss more about that in just a minute. The other topic in this module is abstract algebra. So abstract algebra takes a different approach to the same problems. If we have a set of objects and some operation going on between them, what properties can we guarantee? I often think of this in terms of things like a Rubik's Cube. When we think of the motions of a Rubik's Cube, it turns out the properties related to them are very similar to the properties of real numbers. And understanding that sense of connection can make it so that when we're dealing with other similar objects, we can understand the motions of those objects as well. That said, we want to think of graph theory as an introduction to topology. Topology is one of the major branches of mathematics, not to be confused with topography. Topology is the study of geometry without shape. The idea that when we are considering mathematical objects, sometimes the size or shape of an object doesn't really matter. Uh, One of the jokes is that to a topologist, a coffee cup and a donut are the exact same thing because you can morph one into the other using a few mathematical equations. It's kind of fun and silly, but it's how topology works. And so consider the map to the right. This is actually a map of old school Königsberg. Is it possible to create a path where you cross all of the bridges exactly once? If so, where would you start? If you want, you can try it out right now, and this will be one of the introductory examples in your e-text. But what you really want to think about is when you're doing a problem like this, does the size of the islands actually matter? Does the size of the bridges matter? What about their locations? If we move one a little bit to the left or to the right, will it make a difference? These types of questions kind of give us a way of visualizing this uh, using the idea of vertices and edges instead of with a larger graphic. And when we start to understand that things can be modeled using just points and connectors, it can greatly simplify a problem. That's what graph theory is. And so graph theory is an introductory branch of topology which deals with modeling those type of connections. In the previous problem, the connections were bridges that we were connecting to different islands or regions. But a graph is an object which consists of a finite set of points, which are vertices, and line segments which connect those points. And we can use them to model just about any situation where there are interactions. One example is just this image to the right. This is an image of some folks in a coffee shop. If we look at the individuals in this coffee shop, how are they connected to one another? And so, for instance, we can see that the barista is handing the coffee to someone. We can see that this person and this person are having some kind of conversation. The others might be doing their own thing. We can model those connections using a graph. And here's what a graph might look like. In this case, this is a directed weighted graph. But we can see that in this, there are five different vertices, A, B, C, D, and E. And we can see different connections between them. Once we've established a graph, we can analyze it using various tools. And so is there a directionality to the relationship? There might be, there might not be. Is there a benefit to applying a weight, a number, to the vertices or to the paths? For instance, if you're dealing with money and who owes who money, you can apply a weight to those branches. Are there interesting groupings of vertices or places where introducing paths could improve productivity? If we think of that previous example of coffee house situation, we have these two who are connected, and we have these two who are connected. If we wanted to include everyone in one group, or if we wanted to include everyone in two groups, we could try and figure out simple ways to do that. For instance, connecting the two who are at the table with the other two who are at the table could create one group, and grouping the person in the back with the barista and the person with the coffee could form a second group, and those groups would be similar size. What if instead we wanted to create three groupings out of the same group? How could we do that? And so those are the types of questions which we can ask. And depending on what the application is, we can use graphs to better understand and improve a particular situation. Abstract algebra is in this module as well, but it is a very different approach to things. And so a separate interesting field is abstract algebra. It is a study of sets based on their properties. And we want to go back to like the Algebra 1 properties, the idea of the closure property, the identity property, the associative property, the distributive property, zero product property, all of those old properties that we may or may not remember. Well, it turns out they pop up in very odd locations. And so consider the motions of a clock. 60 minutes is an hour, and every 12 hours, the clock returns to its starting point. Otherwise, the motions of the clock work the same as traditional mathematics. We can add, subtract, multiply, there's negative values, and even an identity element. For instance, if you wanted to get from 1 o'clock back to 1 o'clock, you could add 12 hours and you would be back on the 1 on the clock. If you wanted to go with a 24-hour clock, same thing, but then you would be adding 24 hours to it. If you wanted to go back 5 hours, well, that would be the same as adding 7 hours to the clock, or different with the 24-hour clock. The idea of exploring these properties on more abstract sets is what abstract algebra is all about. In the case of the clock, we would say that it forms what is called an abelian group under the operations of addition, because it satisfies these 5 properties: closure, associativity, identity, inverse, and commutativity. These are some of the more powerful tools out there. And we use this when we're studying other types of objects. One of the biggest applications of abstract algebra is actually in particle physics and trying to understand the motions of atoms. It turns out we can't use traditional mathematics in order to do that, but the fundamental properties are still going to be upheld. And so we can use abstract algebra to understand those motions. Now, I don't know how many folks here are going to be particle physicists, but it is an interesting application. And so we will be introducing the fundamentals of abstract algebra in this course. That said, that is your brief introduction to Module 6, Graph Theory and Abstract Algebra. This is one of my favorite modules, and hopefully you enjoy it too. Good luck, folks.